So, for our next speaker, you're a data scientist at Improve Digital,
Yes.
the real-time bidding company we use for a lot of our advertising.
Yeah.
Still a growing amount, and about approximation algorithm. So,
Correct.
take it away.
So, hi everybody. Thanks for the intro and thanks for inviting me. So, as Sanders said, I'm a data scientist at Improve Digital, and today I want to share with you some lessons that me and my team have learned in building and scaling analytics application using approximation methods. So, I assume that more or less everybody in the audience is a bit familiar with ad tech, but I'll just give, let's say, a brief overview just to set some background so that everybody is in sync. First of all, what is Improve Digital? We are a so-called SSP. That is, we are a platform that connects media owners such as Sanoma to advertisers. Sanoma wants to sell space on websites, advertisers wants to buy space on Sanoma, and we help you guys out. How do we do it? Well, let's do it an example. What happens when you go online, say to nu.nl? Well, on nu.nl you have this space that is normally filled with banners. What happens from the moment you enter the URL to the moment you get your, you see some advertisement displayed is that in the backend, the website makes a call into, in this case, an SSP, such as Improve or other competitors. We get passed a user ID, an identifier of the user at the moment on the website. And we use this UUID to essentially propagate a number of bid requests to advertisers that are also connected in the system. Advertisers can bid on the opportunity of showing a banner to that user, and in real time we determine who is gonna win this auction. And we display an impression, we record the impression, and maybe after a while a user can click on it, they can convert on it, and we also record that kind of event. And all of this auctioning and ad serving happens in about 150 milliseconds or less. Now I think it's 110. And essentially what we do in the backend, we serve ads and we collect a lot of this timestamp data. Right now we are in the order of 200+ billion events per month, being a bit conservative here. This data comes from a geographically distributed ad server fleet. So we have a bunch of ad servers distributed all over the world. And we use the servers to try to serve the impressions as soon as possible. What it means from a data perspective is in time we have hundreds of terabytes in a Hadoop cluster ready to stuff with it. So what do we do with that? Let's say in the data team, that's a team where I'm a member of, we use the data that we collect in terms of events and user interacting with a website or multiple sites to essentially, well, do two things. One, answer questions, might be business or more research type of questions. We try to improve our product by building predictive models that can help us to better serve ad, provide, let's say, ways of helping Sanoma or publisher monetize better their options. And at the same time, we use the data that we collect as a data team to provide and make available resources to other teams. For instance, we can provide roll-ups and, I don't know, aggregate files that are either used in dashboards or in the 360 UI that some of your colleagues use to, well, do their day-to-day operations. So looking at the slides, we have a number of use cases that more often than not essentially result in having to look at the same data, so data coming from ad server in a slightly different way, because we have the use case where we want to analyze, I don't know, a month of data to just compute some simple trends, some simple statistics. There are cases where we want to look in real time or near real time into a stream of data and see what kind of audience, what kind of traffic is coming towards our server. Is it actually a legit user? Is it a botnet? Can we do some filter at that? We need to react quickly in this case. What this means for building applications and analytics is that to perform this, let's say, task at scale, we have some goals in mind. First of all, we want to be able to write jobs once. So we want to have a unified way and essentially a unique code base for analytics and models, because we don't want to have essentially 5 predictive models that do 5 similar things on maybe 5 different data sets with 5 different set of parameters, because, well, that's chaos is ensured. And we want to make jobs that are also scalable, because we want to be able to scale from small data sets to larger data sets, depending a bit on the use case. In principle, we want to unify the concept of batch and real-time data because, I mean, conceptually, everything that we collect comes from a stream of, well, ad server logs. And that's what we want to start to consider as a single source of truth. And from this source of truth, we want to then be able to do some processing, maybe publish some data to other parties, for instance, share some data set with you guys, or embed them into our own predictive models. And another goal that we have is that we want a system, a set of algorithms that enables us to do fast experimentation, meaning we want to go and be able to go from prototyping a model on a small sample to scale it out quickly to a larger and bigger data set. In terms of architecture, the way we started to think and architect our application is a bit as follows. As I said, let's say from our perspective, everything comes from the ad server. So the central point, the single source of truth for our data is real-time log collection. From here, we push ad server log into a brokerage system. We use Kafka, distributed queue, topic-based. We have producers, ad servers that write data into a topic, the impression topic, the click topic, the auction topic. And we have consumers that read data out of this broker system. A nice thing of Kafka is that messages, so timestamp events, are persisted to HDFS, a distributed file system, and at any point in time we can replay the stream of data with variable length time windows, which is really cool because it means we can scale up and down real time or batch depending a bit on what we want to do. From here we can expose topics, so the impression topic, so the click topic can be accessed by applications, and by application I mean a web application, but can also be some kind of machine learning code that can be used to perform analytics on this thing. And in particular, I'm going to show a couple of examples where we're using Spark. For those of you not familiar, Spark is a distributed computation framework that essentially generalizes MapReduce, and it uses some clever engineering for making, let's say, computational scale relatively fast and bypass some of the, let's say, latency issues that are typical in systems such as Hadoop. But I'm going to come to this in a second. And also, from here, once data is processed, we can publish it to a number of, well, endpoint. It can be a database where it can then be picked up and maybe further processed and exposed in 360. Can be HDFS, so that you can use it internally to train model or do other things. Can be, I don't know, in-memory store, such as Redis, because we want to have a cookie store or other kind of stuff. Now, this said, we still have some challenges because, so now that conceptually everything is a stream, how do we go about writing analytics code on a stream of data? In particular, when we start to think about doing analysis on this data set, we have to take into account an application that satisfies a trade-off between latency, because we want to be able sometimes to give answer fast. For instance, fraud analysis, we want to give an answer, is this a bot, yes or no, very quickly. Memory, when we compute analytics on very large data sets, we want to be able to store large amount of data in memory. Well, if we look at a stream with a window of a month, it can become pretty tough to store, I don't know, a few terabytes of data in memory. And accuracy, because depending on how much memory and how much latency we have available, we might want to tune up and down the accuracy of our system. So we want to say that we have a certain amount of impression plus minus a certain confidence interval. And we want to do this on infinitely growing and expanding data sets, because right now everything is a stream, right? So streams, by definition, grows infinitely, hopefully. Well, how do we do this? What we found out is that we need to adjust our approach to analysis and essentially try to make big data small and make the problem a bit more tractable. First of all, making data small, if you've taken some statistics classes or are a bit familiar with analysis, first thing that comes to mind is sampling, right? Yes, that's a very valid point, and turns out that sampling for an infinitely expanding data set with constant memory and in a single pass is not that hard, after all. It's a very known problem. It's a problem that has been addressed in literature since the 80s with techniques such as reservoir samplings that are very simple and very effective. This snippet of code here is something that I'm using in some production code base. Here what I'm doing, I'm enumerating a stream of input. I initialize an empty list. This is Python, so an empty array called sample. This sample has size n. I want to only store n data points out of my stream. And what happens? Data comes in. I start to fill my sample array. Once the elements that are coming in are more than the size that I'm allowing for the sample array, I start to replace elements at random. And here you can tweak a bit, you can be a bit more fancy with distribution, you can account for other distribution or underlying geometry in data and whatnot. And well, it is a sample, essentially. And this works quite well also on a stream, but also if you have a very large data set that you want to process in a kind of iterative fashion and incremental fashion. This is a very simple method that works really well, easy to understand, but it has a couple of problems. It is quite hard to parallelize, and here by parallelizing I mean distributing this sample data structure potentially across multiple processes or threads or across multiple machines. Essentially, we have a central data structure that needs to be locked and updated, and well, engineers in the room might not be really happy to do these kind of things. And also, a sample can only take you so far, in the sense there are some questions that are a bit hard to answer with sample data. For instance, if we want to count the number of unique users on a website, or the top 10 advertiser buying on Sonoma in the last 50 minutes, yes, you can do it with a sample, you can make some estimates, but it needs, let's say, some level of sophistication and statistical understanding that is, I would say, non-trivial in order to get good and reliable results. One way to circumvent this is that, well, we can think about both points from, let's say, a point of view of data structure, and we can turn our sampling problem into a representation problem, right? We can address this issue by using so-called sketching data structure that we can use to store some summaries of our data sets. And these data structures are pretty nice because they can guarantee some good space, accuracy, and time trade-offs, and they are easy to parallelize thanks to some algebraic property. And well, let's dive into some example, and I'll try to show a bit how we do this type of queries. First of all, let's look at cardinality estimation. It's a count distinct. We want to see how many users are visiting a website. Let's say the naive solution for this problem is, well, we can initialize a set or an array or whatnot. We can store user IDs. So every time a user comes to a website, we store an ID. A user can come multiple times, so the same ID might appear multiple times in our set. And then we count the dimension, the length of this array, right? True, can be done, very simple to do, but here we have two challenges. What happens when you have 100 millions or billion of users and your data set grows to a few hundred gigabytes or a terabyte? How do you store this data set in memory in a distributed system, and how do you actually perform computation in maybe in a MapReduce fashion, because you might have your Hadoop cluster and you want to be able to update your stats using Hadoop? Well, turns out there is a data structure that can help us here, and before getting there, well, it relies on some properties of multi-sets. This is a theorem. I call it a claim because I don't give the proof, but I'm going to give you a pointer to the paper where the proof is given, is that the cardinality, so the length of a multi-set of uniformly distributed random numbers, can be estimated by calculating the maximum number of leading zero in the binary representation of each number in the set. Cool? This property of, let's say, set of algebra is exploited into a data structure called hyperloglog. Google actually optimized this data structure, and they called it hyperloglog double-double, and because naming is fun. The joke is, let's see how much words we can use before actually we cannot fit it anymore in the structure. And how does it work? Well, intuitively, it uses a hash function with some good properties. We can get back to details later on if you want, just ping me offline, but it's all described in the paper. And this hash function is applied on each element of the multi-set, and the output of this function is a binary representation of the element that comes in. Then what we do? We look at the binary numbers, binary strings, 0 and 1s that we get out of it, and we make an observation that if the maximum number of leading zeros in a given hash output is n, then the number of distinct elements in the set is 2 to the power of n. It's a bit counterintuitive. Concentrate really hard, and believe me, it works. I'm going to show you in a bit how it works. And plus this data structure also does some, let's say, subsetting and averaging for accounting for variance in the method. The outcome is that we can store a high cardinality set. We can generate very good estimates in the order of 1-2% error rate in about 14K for sets with a few billion elements with the Google paper. I'm not gonna, let's say, show you the algorithm itself, although it's kind of trivial because you just hash and count zeros. I'm gonna show you an implementation that we've done using Spark and a tool called Algebird. It's a library from Twitter that contains a collection of this type of data structure. I initialize an hyperlog, like I would initialize a hash table, a set, or whatnot. And then I'm reading some data from my Kafka topic. I'm reading it from the impression topic. I do some processing where I only extract the impression ID and the user ID, sorry, from my impression. I obtain a stream of data, and then on this stream, I do some map-reduce computation, where in the map phase, I just partition my set across multiple machines. I initialize local hyperlog logs and count the unique user IDs that I've seen in my partition, and then in the reduce phase, I just sum hyperlog logs together. This is really cool because what I'm doing here, I am parallelizing a data structure by splitting into subsets and then taking the union and the sum. This is really non-trivial, and it's a property of an algebraic structure called monoid. Sometimes it comes up as a buzzword, but what's important to remember about the monoid is that it's a mathematically sound abstraction. It's, algebra, let's say, and it has some very nice properties that guarantee that we can parallelize this data structure well and accurately, although with some limitation. The nice thing of doing this stuff with Spark is that this is a case where I'm looking at, for instance, batch data set, where I'm getting data from a topic for a month, but I can reuse the same API and same abstraction for initializing a global hyperlog log, starting to look at a stream as a discretized batch window data coming in. We call it RDD. And then in each time window, in each window data set, I initialize and compute a partial hyperlog log, and then I sum it together into a global hyperlog log, which means I can track users over time. Again, I can do this parallelizing over multiple machines thanks to the good algebraic property of the structure. What it means in practice, it means that we can estimate with 2% error rate and 15 kilobytes of memory. So on the right-hand side, I'm counting the naive method. I'm contrasting the account with the naive method and the approximate method. They look the same. There is a bit of 2% error rate in this estimate. Here I'm looking at an hour and a half of data partitioned into 15 minutes windows. I can see that the memory consumption with my exact method, where I'm storing user IDs into a set, grows linearly, whereas it remains constant in the hyperlog log case. You don't see it very well, but in the exact method, we end up using a few gigabytes, few tens of gigabytes of memory, whereas in the approximate case, we are just flattened out at 15K, which is kind of nice because essentially we make this problem as something that, well, you can do on a calculator these days. Other data structure that we can use for another type of problem, frequency estimation. Especially account managers like to see histograms and plot comparing things. And how are advertisers buying, who is the top 10 list of users, advertisers today, this month, and whatnot. Let's say we call this top-N queries, find the top-N elements, and it's something that we do very often to compare events. And we can do it, for instance, for trend analysis. The naive approach is to use a hash table, store a hash map with all the users, and then, for instance, filter out only the top 10. Again, we can use a data structure to help us out and use a set of pairwise independent hash function that map events into a kind of, let's say, compact representation of my space. And again, by using some clever hashing, we can reduce the dimensionality and essentially store in sublinear space very accurate representation of my data set. Again, I'm not going to get into details. The details are in the paper, but if you've done machine learning, it's a hashing trick. But let's not get there. As before, Algebird has a CMS implementation. CMS is, again, a monoid, distributes very well in MapReduce. As before, works well in the batch case, where I'm counting the number of impressions per publisher in the last 24 hours. And I can do it also over a stream with a very similar API. And here I just want to stress the fact that I'm really reducing code application because I have one API, one implementation, and I just scale it up and down on both cases. This is, These are the results, exact method versus approximate. The error rate is about 0.5%, and you see it only in the tail. The difference is with the exact method, I had to compute, let's say, the frequency of all publisher in our system. With the approximate method, I just restricted the top 15. So I can just filter out the heavy hitters. And qualitatively, it's also clear that these methods, present very actionable information. Finally, I'm just going to wrap it up quickly. Games, but you can do more with this kind of abstraction. In particular, you can use them as a foundation for more advanced methods, such as learning from data. Learning from data, I mean two things, regression and clustering, which are two typical examples of problems where iterative computation, like the stuff you do in MapReduce, does not scale very well. It can be made very scalable, both in literature and, well, there are also some solid implementation of this method by using sketches, coupled with the notion of one pass. Try to limit the number of iteration you need to find a solution by approximating your solution, and also introducing the concept of forgetfulness, both in linear regression and streaming k-means, a popular clustering algorithms that now is also part of Spark. Forgetfulness means that as my data grows, as time goes by, my essentially I want to start to discard some assumption I made in the past and make new one, and essentially keep a fresh memory of what my data sets look like. In conclusion, at Improve, we started to build the application thinking about streaming as part of the broader system. Approximation can help us scale both streaming and batch loads. In principle, we don't want to think anymore about what is streaming and what is batch. We just think of data of, different size and with different constraints. And, essentially, we can analyze this data and make it small and tractable. In all of this, data collection distribution is key. I didn't spend a lot of time on this, but the fact that we have Kafka, the fact that we have Spark really helps a lot in doing these kind of things. Similarly, publishing results is very simple and easy, thanks to Kafka. And finally, for me, the lesson learned is like when I'm thinking about large-scale analytics, it's a combination of architecture, algos, and data structure. And that concludes the presentation.
Okay, we now have a quick break, so if you have any questions, ask it to Gabriele during the break, and we'll be back in 5 minutes. The drinks are in the...